Swayam Prabha. Digital India. Educated India.
Welcome to lecture 6 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Properties of OLS and Maximum Likelihood Estimators. Actually, in the last lecture, we have discussed the multiple linear regression model and different assumptions of the multiple linear regression model. We require all those assumptions to establish the least square procedure for estimating the parameters of the model. If those assumptions are satisfied, then the least square procedure leads to sensible estimators. We also investigated some of the properties of least square estimators of regression coefficients and the disturbances variance. We proved that the resulting estimators are unbiased, and then we have derived the variance covariance matrix of the OLS estimator or variance of the OLS estimator of disturbances variance. We study more properties of the OLS estimator, say finite sample as well as large sample properties of the OLS estimator. We also consider the maximum likelihood estimator for the parameters of the model and investigate their properties. Now, first we proved the best linear unbiased property of the OLS estimator B. So, we state the Gauss-Markov theorem. Suppose lambda is a k by 1 vector with elements lambda 1, lambda 2, lambda k, and then lambda transpose beta is equal to lambda 1 beta 1 plus lambda 2 beta 2 so on plus lambda k beta k. So, lambda transpose beta is a linear parametric function. It is a linear function of different components of beta. Then lambda transpose B is a best linear unbiased estimator or blue of lambda transpose beta in the sense that it is an unbiased estimator of lambda transpose beta, and for any other linear unbiased estimator A transpose y of lambda transpose beta, lambda transpose B has lower variance than A transpose y, that is the variance of lambda transpose B is less than or equal to the variance of A transpose y for all beta. So, now we prove this result. X is a full column rank, that is rank of X is equal to k. Then first we prove the unbiasedness of lambda transpose B. We take expectation of lambda transpose B, which is equal to lambda transpose expectation of B. And in the last lecture, we have already shown that expectation of B is equal to beta. So, we get lambda transpose beta for all. So, lambda transpose B is an unbiased estimator of lambda transpose beta. Now, suppose A transpose y is any other unbiased estimator of lambda transpose beta. So, expectation of A transpose y is equal to lambda transpose beta. On the expectation of y is equal to x beta. So, this gives you expectation of A transpose y equal to A transpose x beta. So, you obtain A transpose x beta equal to lambda transpose beta for all beta, and then from here you get A transpose x equal to lambda transpose or x transpose A equal to lambda. So, you get this relation lambda equal to x transpose A. Then variance of lambda transpose B is equal to sigma square u lambda transpose x inverse lambda, because variance covariance matrix of B is sigma square u x transpose x inverse. So, the variance of lambda transpose B is sigma square u lambda transpose x inverse lambda. Then we take the difference between variances of A transpose y and lambda transpose B. So, variance of A transpose y minus variance of lambda transpose B is equal to, you get sigma square u. Then in the expression for variance of lambda transpose B, we write lambda equal to x transpose A. So, you obtain sigma square u A transpose x transpose x inverse x transpose A. So, you obtain the difference between the variances of A transpose y and lambda transpose B as sigma square u A transpose identity matrix minus x transpose x inverse x transpose A, which is equal to sigma square u A transpose M A, where M is the matrix I minus x transpose x inverse x transpose. Then this M is an idempotent matrix, because M into M is equal to M square is equal to M. And then if we write delta equal to M A, then A transpose M A is equal to M A transpose M A, which is equal to delta transpose delta. Remember that M is symmetric and idempotent matrix. So, variance of A transpose y minus variance of lambda transpose B is equal to sigma square u delta transpose delta, which is always greater than or equal to 0, or we obtain variance of A transpose y greater than or equal to variance of lambda transpose B. So, hence we follow the result. Now, suppose you take lambda I equal to 1 and all other elements of lambda are 0, then lambda transpose beta becomes beta I and lambda transpose B becomes B I. So, for this specific choice of lambda, we observe that B I is the best linear unbiased estimator of beta I, and this holds for all I equal to 1 to k. So, in this sense you can say that B is the best linear unbiased estimator of beta. Now, we prove an alternative form of the Gauss-Markov theorem. Remember that in the earlier form of Gauss-Markov theorem, we have shown that if you have any linear parametric function C transpose beta, then C transpose B is the best linear unbiased estimator of C transpose beta. And this form of Gauss-Markov theorem, we take a linear estimators, beta curl is a linear estimators of beta. So, beta curl is of the form C y and then C is a K cross N matrix. Variance covariance matrix of beta curl is V beta curl equal to expectation of beta curl minus beta, beta curl minus beta transpose. Then variance covariance matrix of B curl minus variance covariance matrix of B is positive semi-definite. So, here we directly compare the variance covariance matrix of this linear unbiased estimator of beta with the variance covariance matrix of B. And then we show that according to this criterion also, the OLS estimator dominates this linear unbiased estimator. So, according to this variance covariance matrix criterion, also the OLS estimator is the best linear unbiased estimator of beta. Actually, in terms of variance covariance matrix, when we say that the estimator B dominates beta curl, we say that B dominates beta curl if the difference between the variance covariance matrix of beta curl and variance covariance matrix of B is positive semi-definite. So, we use this criterion. Now, suppose we write C equal to X transpose X inverse X transpose plus D, where D is any K by N matrix. Then obviously, beta curl is equal to X transpose X inverse X transpose Y plus dy. So, this is equal to B plus dy, where B is equal to X transpose X inverse X transpose Y, and then if we write Y equal to X beta plus U, then this is equal to beta plus X transpose X inverse X transpose U. So, you get beta plus X transpose X inverse X transpose U plus, again we write Y equal to X beta plus U. So, you get d x beta plus d U. Then beta curl is an unbiased estimator of beta. So, obviously, expectation of beta curl is equal to beta. And what is expectation of beta curl? It is equal to beta plus expectation of this term is equal to 0 plus d x beta, again expectation of this term is equal to 0, because expectation of u is 0. So, expectation of beta curl is equal to beta plus d x beta, and for unbiasedness of beta curl, this should be equal to beta, and then this holds for all beta, and this implies that dx is equal to 0. Further, the variance covariance matrix of beta curl is expectation of x transpose x inverse x transpose u plus du, x transpose x inverse x transpose u plus du transpose. We simply take beta curl minus beta from here. So, this is equal to x transpose x inverse x transpose u, then dx beta is equal to 0. So, you get du. So, we write actually variance covariance matrix of beta curl is expectation of beta curl minus beta, beta curl minus beta transpose. Then we have shown that beta curl minus beta is equal to x transpose x inverse x transpose u plus du, and then you have transpose of this. Then the first term is x transpose x inverse x transpose u, u transpose x, x transpose x inverse, and then you have a term d u, u transpose, d transpose. Then you have term, you multiply d u by transpose of this term. So, you get u transpose x, x transpose x inverse, plus you have x transpose x inverse, x transpose u, and then u transpose d transpose. And then we take expectation. So, expectation of this first term is equal to x transpose x inverse, x transpose sigma square u I n x, x transpose x inverse. So, ultimately you obtain sigma square u x transpose x inverse, plus expectation of this term. You have d expectation of u, u transpose is sigma square u I n. So, you get sigma square u d, d transpose. Then you have expectation of this third term, which is d times expectation of u, u transpose x, x transpose x inverse. So, this is equal to, again you get sigma square u I n here. So, you can take sigma square u outside d x, x transpose x inverse, and then d x is equal to 0. So, this term vanishes. Similarly, the expectation of fourth term also vanishes, because it involves x transpose d transpose, which is also equal to 0. If d x is 0, then transpose of this is also 0. So, you obtain this expression for the variance covariance matrix of beta curve. Now, the first term gives you the variance covariance matrix of B. So, you get V B plus sigma square u d, d transpose. If you take the difference of variance of beta curl and variance of B, then V beta curl minus V B is equal to sigma square u d, d transpose. Now, this is a positive semi-definite. So, variance of beta curl minus variance of B is positive semi-definite matrix, and this shows that B is best linear unbiased estimator in terms of variance covariance matrices also. In the class of all linear unbiased estimators, B is the best linear unbiased estimator in terms of the variance covariance matrices. Now, we obtain the maximum likelihood estimators of beta and sigma square u. So, we assume that u follows a normal distribution having mean vector 0 and variance covariance matrix sigma square u I n. Then the maximum likelihood estimators of beta and sigma square u are B equal to x transpose x inverse x transpose y and sigma hat square u equal to V by n, where we have already defined V is equal to y minus x B transpose y minus x B. Now, since u follows a normal distribution, the likelihood function is given by L beta sigma square u equal to summation j product j equal to 1 to n f u j, which is equal to 1 upon 2 pi sigma square u to the power n by 2 e to power minus half value summation u j square. And then using the vector notations, we can write summation u j square as u transpose u, and then u is equal to y minus x beta. So, this is the final expression for the likelihood function, this one. Then the log transformation is monotonic. So, the maximization of the likelihood function is equivalent to the maximization of the log likelihood function. So, instead of maximizing the likelihood function, we take log of likelihood function and then we maximize that log likelihood. Further, we take log of the likelihood function, then log L beta sigma square u is equal to minus n by 2 log 2 pi sigma square u minus 1 upon 2 sigma square u y minus x beta transpose y minus x beta. Actually, this first term we get from here. When you take log of this term, you obtain minus n by 2 log 2 pi sigma square u. And when you take log of this exponential term, then you obtain minus 1 upon 2 sigma square u y minus x beta transpose y minus x beta, that is this term. Then we differentiate the log likelihood function with respect to beta. So, the differentiation of first term is equal to 0, and here we obtain 1 upon 2 sigma square u 2 times x transpose y minus x beta, and we write it equal to 0. Further, we differentiate the log likelihood function with respect to sigma square u, then we obtain, here we get minus n by 2, you can write log 2 pi sigma square u as log 2 pi plus log sigma square u. So, when we differentiate this part, we get 0, and when we differentiate log sigma square u with respect to sigma square u, we get 1 upon sigma square u. So, we obtain minus n upon 2 sigma square u plus 1 square u whole square, and then you obtain this term, and we write it equal to 0. Now, suppose beta hat is the MLE of beta and sigma hat square u is the MLE of sigma square u. Then we obtain beta hat and sigma hat square u by solving these two equations. And from the first equation, we obtain x transpose y equal to x transpose x beta hat. Again, since x transpose x is non-singular, beta hat is equal to x transpose x inverse x transpose y, which is same as the ordinary least square estimator B. So, the maximum likelihood estimator of beta is the same as the OLS estimator of beta, both are identical. Then, to obtain sigma hat square u, we replace this beta hat by B, and then we solve this equation, this second equation, and you can easily verify that sigma hat square u is equal to 1 upon n y minus x b transpose y minus x b, which is equal to v by n, or this is actually equal to n minus k upon n s square, because s square is equal to 1 upon n minus k v. S square is the least square estimator of sigma square u. So, the MLE of sigma square u and the least square estimator of sigma square u are not identical. Further, we obtain the second derivatives of the log likelihood function. So, del 2 or del beta transpose log L beta sigma square u is equal to minus 1 upon sigma hat square u x transpose x. Of course, we replace beta by b and sigma square u by sigma hat square u. Then del 2 or del 2 sigma hat sigma square u square is equal to, that is the second derivative with respect to sigma square u at beta equal to b, sigma square u is equal to sigma hat square u is equal to n upon twice sigma hat to the power 4 u minus 1 upon sigma hat u to the power 6 y minus x b transpose y minus x b. This you can easily verify. We have already obtained the first derivatives here, and you again differentiate this term with respect to sigma square u, and then you replace beta by b and sigma square u by sigma hat square u. So, you get this expression. Again remember that y minus x b transpose y minus x b, this is actually equal to n times sigma hat square u. So, we write it equal to n times sigma hat square u, and then finally, you obtain this second derivative equal to minus n upon twice sigma hat u to the power 4 with respect to sigma square u and beta, at beta equal to b and sigma square u equal to sigma hat square u. And then we obtain minus 1 upon sigma hat to the power 4 u x transpose y minus x b is equal to 0. So, the Hessian matrix of the log likelihood function is, so we denoted by h beta sigma square u, given beta equal to b sigma square u equal to sigma hat square u equal to, you get this matrix of second derivatives, and then we substitute the values of different derivatives at beta equal to b sigma square u equal to sigma hat square u, and finally, you obtain this matrix. So, this Hessian matrix is negative definite at beta equal to b and sigma square u equal to sigma. So, from here we observe that the likelihood function is maximized at these values. So, b and sigma hat square u provide the maximum likelihood estimators of beta and sigma square u. So, note that the MLE of beta is the same as the OLS estimator b, and we also observe that sigma hat square u is not an unbiased estimator of sigma square u, because in the last lecture we have observed that the expected value of y minus x b transpose y minus x b is equal to n minus k sigma square u. So, from here we obtain expected value of sigma hat square u, which is equal to 1 upon n, and then you have expectation of y minus x b transpose y minus x b, which is n minus k sigma hat square u, and then this is equal to 1 minus k by n sigma hat square u. And from here you can easily verify that expectation of sigma hat square u minus sigma square u is equal to minus k by n sigma square u. So, this gives you the bias of the maximum likelihood estimator sigma hat square u of sigma square u. Of course, for large n, if n is very large, then this bias is negligible, because we have n in the denominator. Then we derive the distributions of b and s square. If u follows a normal distribution, then b also follows a normal distribution with mean vector beta and variance covariance matrix sigma square u x transpose x inverse. And if you take v equal to E transpose E upon sigma square u, then this follows a chi-square distribution with n minus k degrees of freedoms. Further, v and b, these two are independently distributed. To obtain the distribution of b, we write in the expression for b, we write y equal to x beta plus u. So, you get b equal to beta plus x transpose x inverse x transpose u. this is equal to beta plus C u, where C is equal to x transpose x inverse x transpose. Again, since u follows a normal distribution, a multivariate normal distribution. So, C u also follows a multivariate normal distribution having mean vector 0, because mean of u is 0, and variance covariance matrix. The variance covariance matrix of u is sigma square u I n. So, the variance covariance matrix of C u is sigma square u C I n C transpose, which is equal to sigma square u C C transpose. And you can easily verify that C C transpose is equal to x transpose x inverse x transpose x x transpose x inverse, which is x transpose x inverse. So, the distribution of C u is multivariate normal with mean vector 0 and variance covariance matrix sigma square u x transpose x inverse. And then actually C u is equal to b minus beta, or b is equal to beta plus C u. So, the distribution of b is normal with mean vector beta and variance covariance matrix sigma square u x transpose x inverse. Further, to derive the distribution of we write E transpose E equal to U transpose M u, where M is equal to I n minus x x transpose x inverse x transpose, and M is an idempotent matrix. It is of course symmetric also. Then for an idempotent matrix, rank of M is same as trace of M, and you can easily verify that trace of M is equal to trace of I n, which is n, minus trace of x x transpose x inverse x transpose, which is same as n minus trace x transpose x inverse x transpose x, which is equal to n minus trace of I k, or you get n minus k. So, since M is idempotent matrix, it has n minus k eigenvalues equal to 1 and remaining k eigenvalues equal to 0. So, you can find an orthogonal matrix P such that P transpose M P is equal to a diagonal matrix with diagonal elements 1 and 0. Actually, these n minus k diagonal elements are equal to 1 and remaining k elements are equal to 0. And we write P transpose M P equal to lambda. So, lambda is a diagonal matrix having first n minus k elements equal to 1 and remaining k elements equal to 0. Now, suppose you write W equal to 1 upon sigma u P transpose u. Now, remember u follows a multivariate normal distribution with mean vector 0 and variance covariance matrix sigma square u I n. So, P transpose u, P is an orthogonal matrix. This also follows a multivariate normal distribution with mean vector 0 and variance covariance matrix sigma square u I n. And if we divide by sigma u, then 1 upon sigma u, P transpose u follows a multivariate normal distribution with mean vector 0 and variance covariance matrix I n. So, W has this distribution. So, the elements of W, that is W 1, W 2, W n are identically independently distributed, each following a standard normal distribution, means each of these W i's follow normal 0 1. Then you can write V equal to 1 upon sigma square u transpose m u equal to W transpose lambda W. And remember that first n minus k diagonal elements of lambda are equal to 1 and remaining diagonal elements are 0. So, you obtain summation j equal to 1 to n minus k W j square, and since each W j follows normal 0 1 and these W's are IIT. So, summation W j square follows a chi-square distribution with n minus k degrees of freedoms. Then finally, we prove that B and V are independently distributed. Then for that purpose, we take expectation of B minus beta mu transpose, which is equal to, you can write B minus beta equal to x transpose x inverse x transpose u. So, B minus beta mu transpose is equal to x transpose x inverse x transpose u, and from here if you take transpose of mu, then you obtain u transpose m, and then we take expectation. So, expectation of u transpose is equal to sigma square I n. So, sigma square u we take outside, then we obtain x transpose x inverse x transpose, here you have identity matrix. So, you get x transpose m, and x transpose m is equal to 0. So, finally, you obtain 0. So, B and mu are uncorrelated and both follow normal distribution. B follows a normal distribution and again u follows a normal distribution. So, mu also follows a normal distribution, which is a linear function of u, and then these are uncorrelated also. This implies that B and mu are independently distributed. Then we can write V equal to 1 upon sigma square u mu transpose mu. So, this is a function of mu. So, since B and mu are independently distributed, B and V are also independently distributed. Further, we obtain the variance of S square. Remember that S square is equal to E transpose E upon n minus k, and then you can write it equal to sigma square u upon n minus k E transpose E upon sigma square u. So, variance of S square is equal to square of this quantity sigma u to the power 4 upon n minus k square, then variance of E transpose E upon sigma square u, and E transpose E upon sigma square u follows a chi-square distribution with n minus k degrees of freedoms. So, its variance is equal to 2 times n minus k. So, finally, you obtain variance of S square equal to 2 times sigma u to the power 4 upon n minus k. Now, we obtain the Cramér lower bound for the variances. So, the matrix of second derivative of log likelihood function with respect to beta is minus 1 upon sigma square u x transpose x, and then we take expectation of this. So, we get the same matrix. Then we take the second derivative of log likelihood function with respect to sigma square u. So, we obtain n upon 2 sigma u to the power 4 minus 1 upon sigma u to the power 6 y minus x beta transpose y minus x beta, and then we take expectation of this. And notice that expectation of y minus x beta transpose y minus x beta, actually y minus x beta is equal to u. So, this is equal to expectation of u transpose u, and this is equal to n times sigma square u, or you can write it as expectation of summation j equal to 1 to n u j square, and each of these u j's have variance sigma square u. So, expectation of u j square is equal to sigma square u for all j, and then you obtain n here. Then expectation of del 2 log L beta sigma square u del sigma square u is equal to expectation of minus 1 upon sigma u to the power 4 x transpose y minus x beta, which is equal to 0. So, the Kramer-Rao lower bound for the variance of unbiased estimators of beta sigma square u is I n beta sigma square u inverse, which is equal to minus expectation of the Hessian matrix and then inverse of this. So, this is equal to, we substitute this expression from all these expressions. So, finally, you obtain this matrix. So, from here we observe that the Kramer-Rao lower bound is attained for the variance covariance matrix of B, because this is the same as the variance covariance matrix of B, but not for variance of S square. Here you do not get the variance of S square. So, it is not attained by the variance of S square. Now, we investigate the large sample properties of the least squares estimator. So, we prove the consistency of these estimators. For that purpose, we assume that this x j u j for j equal to 1 to n is a sequence of IID random variables, where this x j is actually the jth observation on all the explanatory variables. This is the vector of jth observation on all the explanatory variables. And then we also assume that x transpose x upon n has the probability limit q as n tends to infinity, and this probability limit exists and is a non-stochastic positive definite matrix with finite elements. So, this q has finite elements. Then under those assumptions, the OLS estimator B is a consistent estimator of beta, and S square is a consistent estimator of sigma square u. So, now we prove this result. So, we can write B equal to beta plus x transpose x inverse x transpose u, and then we divide x transpose x by n, and then we divide x transpose u by n here. Now, we have already assumed that as n tends to infinity, 1 upon n x transpose x tends to q. Then 1 upon n x transpose u is equal to 1 upon n summation j equal to 1 to n x j u j. So, this is equal to summation j equal to 1 to n w j, where w j is equal to x j u j. In fact, you observe that this x j is the jth column of x transpose, and then 1 upon n summation w j is equal to w bar. So, probability limit of B is equal to beta plus the probability limit of 1 upon n x transpose x is q, or the probability limit of 1 upon n x transpose x inverse is q inverse, and then you have probability limit of w bar. Further, expectation of w j given x is equal to x j expectation of u j given x, and this is equal to 0. So, this implies that expectation of w bar is equal to 0. Again, the variance covariance matrix of w bar is expectation of w bar transpose given x equal to your w j is actually equal to x j u j. So, expectation of w bar transpose is equal to 1 by n expectation of summation x j u j summation x j transpose u j. And when you take product of these two summations, so you get square terms, u j square has expectation sigma square is u. In fact, we get 1 upon n square here, we get 1 upon n from here and 1 upon n from here, and the cross product terms have expectation 0. So, you get 1 upon n square sigma square u summation x j transpose, and then 1 upon n, actually summation x j transpose is same as x transpose x. So, you get sigma square u upon n 1 upon n x transpose x, or you can say variance of w bar is equal to sigma square u by n expectation of 1 upon n x transpose x. Then we have already assumed that 1 upon n x transpose x has probability limit q. So, this converges to a finite matrix, and as n tends to infinity, this term tends to 0, sigma square u upon n tends to 0. So, limit n tending to infinity variance of w bar is equal to limit n tending to infinity sigma square u expectation 1 upon n x transpose x, and this term has probability limit q, which is a finite positive definite matrix. Limit n tending to infinity sigma square u upon n is equal to 0. So, limit n tending to infinity variance of w bar is equal to 0. So, probability limit of 1 upon n x transpose u is equal to 0, and this implies that the probability limit of B is equal to beta. So, B is a consistent estimator of beta. Then we can write S square as 1 upon n minus k u transpose m u, which is equal to n upon n minus k 1 upon n u transpose u, because n is equal to I n minus x, x transpose x inverse x transpose minus you take 1 upon n u transpose x, then 1 upon n x transpose x inverse from here, and then 1 upon n x transpose u. Again, as n tends to infinity, n upon n minus k tends to 1. Further, probability limit of 1 upon n u transpose x, 1 upon n x transpose x inverse, 1 upon n x transpose u is equal to 0, because this tends to a finite matrix and probability limit of this is 0, probability limit of this is 0. So, ultimately this entire expression has probability limit 0. For the probability limit of 1 upon n u transpose u is equal to probability limit of 1 upon n summation j equal to 1 to n u j square, and u j square are IID with common mean sigma square u, means expectation of u j square is equal to sigma square u for all I. So, by using the central limit theorem, actually 1 upon n summation j equal to 1 to n u j square is the mean of u j squares. So, this converges to expectation of u j square, that is sigma square u. So, probability limit of 1 upon n u transpose u is sigma square u. So, probability limit of s square is equal to sigma square u. So, s square is also a consistent estimator of sigma square u. Then we observe that the asymptotic variance covariance matrix of B is n times the probability limit of sigma square u 1 upon n x transpose x inverse. In fact, the variance covariance matrix of B is sigma square u x transpose x inverse, and then you can write it as n times sigma square u 1 upon n x transpose x inverse, and then we take the probability limit. So, you get this expression. Further, if you take the probability limit of s square 1 upon n x transpose x inverse, this is equal to sigma square u q inverse. So, obviously, an estimator of the asymptotic variance covariance matrix of B is s square x transpose x inverse. So, in this lecture, first we have established the blue properties of the OLS estimator. We have shown that in the class of all linear unbiased estimators, the OLS estimator is the best in the sense that it has minimum variance. Then we have derived the maximum likelihood estimators of beta and sigma square u, assuming that the disturbances follow normal distribution. And we observe that the MLE of beta is same as the OLS estimator of beta, but MLE of sigma square u is different from the OLS estimator of sigma square u. In fact, MLE of sigma square u is a biased estimator. Then we have derived the distribution of OLS estimators, and we require the distribution of these estimators for testing of hypothesis. Particularly for testing of hypothesis, we require all these distributions of B and S square. Then we have shown that the OLS estimators B and S square are not only unbiased, but in large sample these estimators are consistent also. So, we have proved the consistency property of these estimators. We have also shown that the variance covariance matrix of OLS estimator of beta attains the Cramer-Rao lower bound, but the variance of S square does not attain the Cramer-Rao lower bound. Apart from the properties of these estimators, we also require some measures of goodness of the model. So, here I am going to stop. Thank you.
Hello, I am Shikha Dikshit. I teach psychology and I work with the Department of Humanities and Social Sciences at IIT Kanpur. Today I will talk about what is causal attribution or how do people understand causes of behavior. Causal attribution is one of the major topics in social cognition in psychology, and this refers to the fact that people attribute causes to their own behavior as well as to behaviors of others. So, understanding the antecedent conditions of behaviors and events is one of the major topics in social cognition. Causal attribution is about finding explanations, and these explanations serve a functional purpose since they are useful in the purpose of planning of behavior and regulation of responses. As far as attribution of causes is concerned, generally people either do internal attribution or external attribution. Internal attribution when causes are understood in terms of internal characteristics of people, and external attribution when causes are understood in terms of contextual and situational features. The main perspective that is employed in the understanding of causal attribution is the naive scientist perspective, and this has emerged from the research on attribution itself, and it views attribution process as a detailed and systematic causal search. And this is the dominant view about understanding attribution in social cognition. However, in recent time this is not the only view, there are alternative views also which try to understand how people make quick judgments about causality. So, now the question is that why is it that people make causal attributions? The answer to this question can be provided in terms of need for prediction and control. People need to predict their environment, and hence it is important for them to understand antecedent conditions of any behavior or any event. Also, causal analysis is related to various other processes other than attribution. It also becomes the basis of regulation of responses. People also develop causal theories based on their experience, and they employ these theories in different domains. As far as attribution theory is concerned, it consists of mainly three theoretical formulations. One is the Heeder's theory of naive psychology, the other one is Jones and Davis's correspondent inference theory, and the third one is Kelly's covariation model and causal schemas. There are other areas of psychology also from where some principles have been picked up and extended to understanding of causality. These areas are emotions, self-perception as well as personality. Psychologists have also tried to understand attribution in specific domain areas. Psychologists have tried to outline the different dimensions that people use to understand causality in domains such as achievement domain, that is understanding causality regarding achievement related behavior such as success and failure, depression, helping behavior as well as close relationships.